Kita dah selesai untuk chapter 1, chapter 2 dan kali ni kita masuk ke chapter 3. So chapter 3 dan 4 ni dia mengenai vektor. So chapter 3 ni introduction daripada vektor. Di chapter 4 tu dia complicated sikit lah. Okay, dalam video ni biasanya saya buat dalam kelas online So saya macam asyik tengok saya je mengajar. So saya nak minta bantuan orang lain pula mengajar. So dalam video ni bukan saya mengajar saya sebagai moderator saja. Okay, so dalam 31 ni the graph of vector value function ni. Okay, what is the vector value function? Okay, kita dengar dulu daripada seorang yang pakar dalam matematik ni.
So far with line integrals has been with scalar functions or scalar valued functions, and when I say that, that just means you give me an x and a y and you evaluate the function at that x and y and you get another scalar value. You get just a number. You don't get a vector. So what I want to do in this video is start to get ourselves warmed up with regards to vectors so that we can understand what it means to take a line integral with vector valued functions. So let me write down some vector valued functions. Actually, even a better place to start, let me draw a curve, or let me describe a curve. So let's put that little f of x, y to the side. We can ignore it for now. Let's say I have some curve C, and it's described. It can be parameterized. I can't say that word. As let's say x is equal to x of t, y is equal to some function y of t. And let's say that this is valid for t is between a and b. So t is greater than or equal to a, and then less than or equal to b. So if I were to just draw this on a, let me say, I could draw it like this. I'm staying very abstract right now. This is not a very specific example. This is the x-axis, this is the y-axis. My curve, let's say this is when t is equal to a. And then the curve might do something like this. I don't know what it does. Let's say it's over there. This is t is equal to b. This actual point right here will be x of b. That would be the x coordinate. You evaluate this function at b, and y of b. And this is, of course, when t is equal to a. The actual coordinate in R2 on the Cartesian coordinates will be x of a, which is this right here, and then y of a, which is that right there. And we've seen that before. That's just a standard way of describing a parametric equation or curve using two parametric equations. What I want to do now is describe this same exact curve using a vector valued function. So if I define a vector valued function, and if you don't remember what those are, we'll have a little bit of a review here. Let me say I have a vector valued function r. And I'll put a little vector arrow on top of it. In a lot of textbooks, they'll just bold it, and they'll leave scalar valued functions unbolded, but it's hard to draw a bold, so I'll put a little vector on top. And let's say that r is a function of t. And these are going to be position vectors. Position vectors. Position vectors. And I'm specifying that because in general, when someone talks about a vector, this vector and this vector are considered equivalent as long as they have the same magnitude and direction. No one really cares about what their start and end points are, as long as their direction is the same and their length is the same. But when you talk about position vectors, you're saying, no, these vectors are all going to start at 0 at the origin. And when you say it's a position vector, you're implicitly saying this is specifying a unique position. In this case, is going to be in 2-dimensional space, but it could be in 3-dimensional space, or really even 4, 5, whatever, n-dimensional space. So when you say it's a position vector, you're literally saying, okay, this vector literally specifies that point in space. So let's see if we can describe this curve as a vector, a position vector valued function. So we can say r of t, let me switch back to that pink color. I'll just stay in green, is equal to x of t times the unit vector in the x direction. The unit vector gets a little caret on top, a little hat. That's like the arrow for it. That just says it's a unit vector. Plus y of t times j. If I was dealing with a curve in 3 dimensions, I would have plus z of t times k. But we're dealing with 2 dimensions right here. And so the way this works is you're just taking your, well, for any t, and and still we're going to have t is greater than or equal to a, and then less than or equal to b. And this is the exact same thing as that. Let me just redraw it. So let me draw our coordinates. Our coordinates right here, our axes. So that's the y-axis, and this is the x-axis. So when you evaluate r of a, right, that's our starting point. So let me do that. So r of a, maybe I'll do it right over here. Our position vector valued function evaluated at t is equal to a is going to be equal to x of a times our unit vector in the x direction plus y of a times our unit vector in the vertical direction, or in the y direction. And what's that going to look like? Well, x of a is this thing right here. So it's x of a times the unit vector. So it's really, maybe the unit vector is this long. It has length 1. So now we're just going to have a length of x of a in that direction. And then same thing in y of a. It's going to be y of a length in that direction. But the bottom line, this vector right here, if you add these scaled values of these two unit vectors, you're going to get r of a looking something like this. It's going to be a vector that looks something like that. Just like that. It's a vector. It's a position vector. That's why we're nailing it at the origin, but drawing it in standard position. And that right there is r of a. Now, what happens if a increases a little bit? What is r of a plus a little bit? And I don't know, we could call that r of a plus delta, or r of a plus h. We do it in different colors. So let's say we increase a little bit. R of a plus some small h. Well, that's just going to be x of a plus h times the unit vector I plus y times a plus h times the unit vector j. And what's that going to look like? Well, we're going to go a little bit further down the curve. That's like saying the coordinate x of a plus h and y plus a plus h. It might be that point right there. So it'll be a new unit vector. It'll be a new unit vector. Sorry, it'll be a new vector, position vector, not a unit vector. These don't necessarily have length 1. That might be right here. I'm going to do that same color as this. So it might be just like that. So that right here is r of a plus h. So you see, as you keep increasing your value of t until you get to b, these position vectors are going to keep specifying. We're going to keep specifying points along this curve. So the curve, let me draw the curve in a different color. The curve looks something like this. It's meant to look exactly like the curve that I have up here. And for example, r of b is going to be a vector that looks like this. It's going to be a vector that looks like that. I want to draw it relatively straight. That vector right there is r of b. So hopefully you realize that, look, these position vectors really are specifying the same points on this curve as this original, I guess, straight up parametrization that we did for this curve. And I just want to do that as a little bit of a review, because we're now going to break into the idea of actually taking a derivative of this vector valued function. And I'll do that in the next video.
Saya harap faham lah penerangan tu. Itu baru introduction vektor tu. So kali ni pula bukan saya yang akan menerangkan tentang develop parametric equation. So tadi seorang Mak Saleh lah sebenarnya bukan Mak Saleh, dia seorang Indian guy. So kali ni seorang ladies pula yang akan terangkan macam mana nak develop parametric equation.
Hey guys, it's Cassie here with Math OMG. Today we're going to be learning how to find parametric equations for a line given 2 points. So if we look at this problem, the first thing that we notice is we're given an a and a b coordinate. A is -2, 3, and b is 3, 6. Our goal is going to be to take these 2 points and make a parametric equation, which means put each equation in respect to t with y and x. So the first thing we need to look at is what's our initial and what's our terminal point. So our initial point in this case is going to be the first given value, which is a, and our terminal point is b. And then we are going to create 2 equations. So a parametric equation means we have x equals something with respect to t and y equals something with respect to t. Now here are kind of the way that I like to think about it. This will not be found in a textbook, or at least not any of the textbooks that I looked at, so don't try to go and like find these equations somewhere else. This was just the way that it seemed most logical to me. So this is kind of how I set it up and then how I teach my students how to do it. So the first thing we have to do is find an equation with respect to x and t. So it's going to be in this format, which looks very similar to when you are finding slope-intercept form of a linear function. You have your variable, in this case x, equals your initial amount plus some, we can call it slope, times t, and then you also have an equation with respect to y and t. And then we need to figure out, okay, so when t is 0, my x needs to be -2, my y needs to be 3, so that means my x for this equation and y for this equation. And then when t equals 1, my x needs to be 3 and my y needs to be 6. And these numbers right here, the 0 and 1, will always be the case in every textbook I've looked at. That's always the case, is we're trying to figure out between those two parameters of 0 and 1. We're trying to figure out that line. And then our game plan for doing this is just going to be to use these formulas. So as we go through and write this, the first thing I'm going to do is separate this. So I need to make an equation for an x equals and for a y equals. Now this a1 for x, and I'm going to write this down. So I'm just going to write down all the information I need so that I'm not confused going back and forth. I need to figure out in my equation, which is a1 plus wt, I need to make an equation, so I need to find a1 and I need to find w. And I need to know these facts. When t is 0, my x is supposed to be -2, and when t is 1, my x is supposed to be 3. And I got those from these equations. So this part right here represents your x, and then the second coordinate represents your y, just like in a normal xy point. So my a1 is pretty easy. It's always my initial point x value. So the initial was a, and the initial x value of point A is -2. So a is -2. And then w, I don't know, but I do know that I have a t value of 1 when x is 3. So if I know those 3 unknowns, then all I have to do is solve for w. So when x is 3, a1 is always -2, so that's going to stay -2, plus w times time, or t, not time, t, which is 1. And then I just solve for w. So 3 equals -2 plus w. W times 1 is w. Then I add 2 to both sides, and I get w equals 5. So the equation for x is going to be x equals my initial x value, which was -2, plus w, which I solved for to be 5, times t. So that is my parametric equation for x. Then I do the same thing for y. So y is equal to b1 plus zt. And again, I have similar restrictions. So my b1, that's my first initial x or y value, sorry, my y value. So I'm going to say that is 3. And then I have a z that I don't know. So I'm going to write down z. I'm trying to find that. I don't know that. And then I also know that when t is equal to 1, my y value needs to equal 6. So again, I plug all of that information in, and then I solve for z. So y is 6, b1 is 3, z is unknown, and t is 1. So then it's 6 equals 3 plus z. I subtract 3 from both sides. 3 is equal to z. So this equation for y is y equals our initial y value, which is 3, plus z, which is 3t. So here are my two parametric equations, right here and right here. Those are my parametric equations. Now, if it asked me to do this for a line, then I would say that these are my two equations, and that my t is going to be from negative infinity to infinity, which should make sense. You want your line to go on forever, so your t values need to go on forever. That's how you create a line. To create the line segment, we just want the line segment between those 2 points. So then the line segment between those 2 points is going to be between these two t values that we created the line with. So for the line segment, we would say t needs to be in between 0 and 1. And that's it. We've created parametric equations of a line given 2 points. Thank you so much for watching.
Dia terangkan tentang parametric equation. Untuk video seterusnya pula akan diterangkan tentang vector equation pula.
Okay, in this video I just want to talk about finding vector equations of lines. And the idea, the formula is, so the vector R, if it goes through the point little x sub 0, y sub 0, z sub 0, and we want the equation of the line with some, some given direction, the formula for that is we use r sub 0 plus t times some vector v. And two things here. The idea is v is parallel to the line. Okay, so vector v is just any vector that has the same direction as the line that goes through the point. It can be any length that it wants to be as long as it's parallel. And this r sub 0 is just a position vector that points at the point that the line should go through. Okay, so I don't know if it's worth mentioning kind of the way that I remember this. So let me erase my picture. If you think about point slope formula, y equals mx plus b, I'm going to write it as b plus mx, or I could write it as b plus xm. So instead of writing y equals mx plus b, I'm going to rewrite it like this. It's kind of analogous to me. It's not, it's not the same, but this is a way for me to remember it. In slope-intercept, b is a point that the line goes through. Well, it's actually a very specific point. It's the y-intercept. And instead of the y-intercept, now we're just kind of using a generic, again, it's a position vector. But to me, I think basically instead of b, we're using sort of a point on the line. And okay, so t is our variable. We usually use t when we use variables for vectors. So instead of our variable x, we have our variable t. M represents the slope of the line. In 3 dimensions, we don't talk about slopes, but this vector v is parallel to the line. So just like m sort of tells you the direction of the line, the slope tells you the direction, which way you're going. This v that's parallel to the line, it's also going to specify the direction that the line's going. Okay, so I don't know. At least that's how I remember it. Maybe it's just confusing, who knows. But okay, so let's do 2 problems here. We're going to find a vector equation for the line that goes through this point 1, 0, negative 3, and is parallel to the vector 2i minus 4j plus 5k. And then we're just going to find a vector equation for a line that goes through 2 points. So 2 problems, neither of which I think are going to be hopefully too terribly miserable. So in the first problem here, give myself a little room. So I can remember my other problem here because I'm about to erase it. The first one is really very easy. So it says our vector v is going to be a position vector that points to a point plus t times a vector v that's parallel. Well, we know that this point 1, 0, negative 3 is on our line, so the position vector that would go to that point would be 1, 0, negative 3. We drop in our t, and now it's easy. Again, we need a vector v that's parallel, but they tell us that, we're given for free that this vector is parallel. So we can, remember, we can write it in component form as 2, negative 4, and 5. So that's all I'm going to drop in there. 2, negative 4, and 5. And if you want to, you could rewrite this. So this is 1, 0, negative 3. Remember, if you multiply out front, you have to distribute, so the t will get distributed to everything. So we get negative 2t minus 4t, and then we'll get 5t. And with vectors, you add them each component, so we'll get simply 1 minus 2t, we'll get negative 4t, and then when we add, we'll get negative 3 plus 5t. So this is a vector equation that represents the line that goes through the point 1, 0, negative 3 and is parallel to the specified vector. You could even specify, sometimes they'll ask about the parametric equations for the line. So the 1 minus 2t, that would be the parametric form for the x-coordinate. Negative 4t would be the parametric form for the y-coordinate, and negative 3 plus 5t would be the parametric form for the z-coordinate, just in case somebody asks that or you see that in a problem. No big deal. Okay, so let's do our other problem here real quick. So now we simply want the vector that goes through the point 1, 3, 2, and negative 4, 3, 0. Okay, so already when I fill in my vector equation, I can use either one of these points. So I'll just use the 1, 3, 2. And then we need our plus t times, well now we need a vector that's parallel. But remember, if our vector goes from the point 1, 3, 2, the direction here doesn't matter at all, so I'm just going to pick one, to the point negative 4, 3, 0. Remember, to find this vector, we simply subtract respective components. So I would take negative 4 minus 1, 3 minus 3, and 0 minus 2. So it looks like to me we would get negative 5, 0, negative 2. That would be the equation of the vector that connects the point 1, 3, 2 to negative 4, 3, 0. Well, certainly it's parallel to the line that goes through the 2 points. So now I can just use this negative 5, 0, negative 2 as my parallel vector. So I'll simply drop that in there. Negative 5, 0, negative 2. And again, if you wanted to, you could do the same thing. So you would get 1 minus 5t. It looks like we would get 3 plus 0t. And then we would get 2 minus 2t as an equation for the line that goes through those 2 points. Okay. Alright, nothing too bad, you know. It's, again, to find the equation of a line, all you need basically is you need a point that goes through the line, and instead of writing it in the point form, you just write it as a vector. And again, the only other thing you need, instead of the slope, we just need the direction that the line is facing, and that's what this other vector tells us. So, alright, I hope this video makes some sense. If you have any questions or comments, as always, feel free to...
Seterusnya, kita akan tengok pula bagaimana kita nak sketch. Sketch ni maksudnya kita nak lukislah kan, the graph untuk vector value function pula. Okay, yang ni contoh untuk line.
Two ways of doing this. There's a way of that was just suggested, where you eliminate the t, or you can actually go straight to it. Alright, so let x, well I guess I'm going to hedge my bets there. We either have it or we're going to let it be. X equals t, y equals t plus 2. We eliminate t to get a basic line. Okay, it's not that hard. Can anyone suggest another way of doing that problem? Maybe even a quicker way? This is kind of the let's just grind through it way. Is there a slightly more enlightening way to do it? Yes. Oh, okay, all right. Sorry, when you put your hand up, I'm late. Okay, well, let me show you. all it is rearranging the vector function. So if I just write it out like this, we get the vector parameterization for a line in 2 dimensions. Okay? It's got to go through the point 0, 2, and it's got to be parallel to the vector 1, 1. So that's 2 ways. So that's 2 ways of solving the problem. This one's pretty quick. I've got to say I like that one. All right? So what would our line look like? Something like that. Okay, pretty straightforward.
Okay, boleh faham? Simple je kan? So yang ni contoh pula nak sketch untuk graf, tapi ni yang involve sin and cos. Ini video ni yang paling saya suka lah.
One of the more challenging things is sketching a vector-valued function in 3 dimensions. There are a couple different ways to go about it. Some of them have recognizable forms, like this one. Could we plot points? Absolutely. But here we see we have a familiar form in my x component and my y component. That's the parameterization of a circle. A circle, sure, whose radius is 4. So in my xz, I have a circle. That's right here. What do you notice in our y-coordinate? That sucker's linear, huh? Sure. So we have a circle in our xz, and then it's going to go linearly on y. If we take a look at this, my trace in the xy plane, it's going to be a cosine wave? Sure. Cosine going down y. In my xz plane, it's going to be a circle. So if we were standing down y and we were looking at xz, we're going to see a circle. Here, if I was standing on z and I was looking down at the plane, I would see a cosine wave. And here, if I was standing on x, or looking down x into the yz, we see a sine wave. Good times. Let's go ahead and graph this guy. Where is it at time 0? R0.
This is 4 cosine 0, 0, sine 0, or 4 times. So what's the cosine of 0? Yeah, that'd be 1. Fun. Yes. So it's going to be at 4, 0, and the sine is 0? That's 0.
So it's going to be 4 on the x. Zero on the y and 0 on the z. Maybe you want to plot another point. Plot another point. How about r of, what's going to be nice? You want to use pi over 2? Pi over 2.
So then, this is 4 cosine pi over 2, pi over 2, and 4 sine pi over 2. Sure, cosine pi over 2. That thing's 0. Then we're going to have pi over 2 on our y, and then on our z, we see that we have 4. Sure. So if we're going to put that point, x is 0, y is pi over 2. That's a little bit over 1.5. So if that's 4, 1.5 is here. And then where is it? It's 4 on the z. 4 on the z. Sure. So it's 0 on the x. Pi over 2 here. And up 4 up there. So we see our spiral is going like this. down.
Z. And when you do these sketches, you need to include your orientation. And of course it doesn't loop over, it's because it's all 3D and stuff. Okay, so you're going to see it's going to be traveling along a cylinder whose radius is 4. On the outside, of course. In a linear fashion.
Okay, seterusnya inilah last video untuk this kuliah, this lecture is how to develop vector equation. So ini intersection between two surface. Okay.
Welcome to a video on space curves represented by the intersection of surfaces. The goal of this video is to determine the intersection of two surfaces and then express the intersection as a vector valued function. Let's take a look at our first example. Here we want to graph the two surfaces and then determine the equation of the intersection using a vector valued function. Let's start by taking a look at the graph of these two surfaces. We can see we have a paraboloid and a plane. Let's angle this so we can get a good idea of what the intersection looks like. We can see here that the intersection is a circle, but it's shifted up 1 unit on the z-axis. So let's go back and figure out how we can determine what the equation of this circle would be. What we're going to do is find a solution to this system using a set of parametric equations, and then once we have the parametric equations, we're going to rewrite it as a vector valued function. So since the intersection is a space curve, in parametric form we're going to have an equation for x of t, y of t, and z of t. We want these three equations to satisfy both of these equations. Well, right away we know that z has to equal 1 based upon this second equation. So now we know that z of t must be 1, and we can use this to perform substitution into the first equation. So replacing z with 1, we would have 1 equals x squared plus y squared. So now we need to determine what we could use for x and y in terms of t to satisfy this equation. Well, whenever we see something like this should remind us of the trig identity sine squared theta plus cosine squared theta is equal to 1. So using that identity, we could let x equal cosine t and y equal sine t. And if we perform substitution here, we'd have cosine squared t plus sine squared t, and this does equal 1. So both of these equations are satisfied with these three parametric equations. So the intersection of these two surfaces expressed as a vector valued function. In component form, the x component would be cosine t, the y component would be sine t, and the z component would be 1. Of course, we could also express these as a sum of the unit vectors I, j, and k, but I'm going to go ahead and leave it in component form. Let's go and take a look at another example. Again, we want to graph the two surfaces and then determine the equation of the intersection using a vector valued function. We have x squared plus z squared equals 4 and y equals z squared. Here's the graph of the two surfaces. If we rotate this around, we can see the intersection of these two surfaces is outlined here in green. And our job is to determine the equation of the vector valued function that represents this intersection. So let's go back and do it. Because it's a space curve, if we can define x of t, y of t, and z of t that satisfy both of these equations at the same time, we can then rewrite these equations as a vector valued function. So looking at this first equation, we have x squared plus z squared is equal to 4. Well, if this was equal to 1, we could let x equal cosine t and z equal sine t, but it's not, it's equal to 4. So in this case, if we let x equal 2 cosine t and z equal 2 sine t, this would satisfy the first equation, because if we square 2 cosine t, we would have 4 cosine squared t. And if we square 2 sine t, we'll have 4 sine squared t equals 4. If we factor out the 4, we have the identity that we want, cosine squared t plus sine squared t, which is equal to 1 and satisfies that first equation. So now we're left with satisfying the second equation given that y is equal to z squared. Well, if we defined z as 2 sine t, we can just square z to get y. So we can define y as 4 sine squared t, which means the intersection of those two surfaces as a vector valued function would have an x component of 2 cosine t, a y component of 4 sine squared t, and a z component of 2 sine t. Now I should make a note that these parametric equations could be defined in a different way, meaning we could have let x of t equal 2 sine t and z of t equal 2 cosine t, which would have changed y of t. So the way of expressing this vector valued function is not unique, but it does satisfy these two equations, and therefore it does represent the intersection of those two surfaces. Here we have x squared over 9 plus y squared over 16 plus z squared equals 1 and y equals x squared. And we only want to consider this when z is greater than or equal to 0. So notice that I'm only including the graph above the xy plane, and again we can see the intersection would be this curve here. And again, our job is to determine what that equation would be as a vector valued function. So we'll first express the solution as a set of parametric equations, so we'll need x of t, y of t, and z of t. Now this does not remind us of any trig identity that we're aware of, so this one is going to take a little bit more work. Let's take a look at the second equation first. If we have y equals x squared, if we let x equal t, that would make y t squared. So these two equations satisfy the second equation. Now we're left trying to satisfy this first equation in terms of x, y, and z. But now that we've already defined x and y, let's go ahead and perform substitution in for x and y. So x squared would be the same as t squared. So we'd have t squared over 9 plus y squared would be t squared squared, or t to the 4th, over 16 plus z squared is equal to 1. Now we are looking for a way to express z as a function of t. Notice this equation now only has t's and z's. So if we solve this equation for z, it would be a function of t. So let's go ahead and do that. We're going to go ahead and subtract these two terms to the right side. So we'd have z squared equals 1 minus t squared over 9 minus t to the 4th over 16. And now we can take the square root of both sides. And because we're only considering z greater than or equal to 0, we're going to use the principal square root here. We're going to have z equals the square root of 1 minus t to the 2nd over 9 minus t to the 4th over 16. And I'm going to go ahead and leave it like this. So now we can express z as a function of t. Which means we can now express the intersection of these two surfaces as a vector valued function, where the x component is t, the y component is t squared, and the z component is the square root of 1 minus t to the 2nd over 9 minus t to the 4th over 16. Okay, that's going to do it for this video. I hope you found it helpful.
Okey, seperti biasalah so dia ada individual work 3, 1. So ada 4 soalan sini, tapi vektor ni dia punya jalan kira sikit dia tak macam chapter 2 yang panjang Jalan kira dia agak simple sikit lah. So boleh try buat lah kalau tak tahu boleh tanya.